Okay, in this video I'm going to cover the extra material for section 2.3, and it will give us a chance to go over some more of the first and second derivative tests and some curve sketching. So up to this point we worked with problems with unconstrained domains, so they weren't really word problems. So now I'm going to introduce 3 word problems that have some built-in constraints on it, and the constraints are on the x values or the domain. Okay, so here are the directions, what we're going to do right here. So let's look at the first problem. So I'm going to slide this up a little bit. Here we go. Okay, the first problem says you have a company and it's found that its weekly profit from the sales of X units of an auto part is given by this equation. So here's weekly profit. Production bottlenecks limit the number of units that can be made per week to no more than 150. So that is the edge of your domain. Okay, so this is 150 is as high as your X value can go. And then it goes on to say, while a long-term contract requires that at least 50 units be made each week. Okay, so 50 is the low. So here are your domain constraints. So now they want us to find the maximum possible weekly profit that the firm can make. Okay, so to maximize profit, we're going to take the first derivative just like we always have, and that first derivative is going to be negative 0.06 x squared plus 600. Okay, so we're going to set that equal to 0, and you're going to end up getting that x squared equals 10,000. So if x squared equals 10,000, then taking the square root of both sides gives you x equals plus and minus 100. Okay, so a word about this. You have to omit negative 100 because it's not in your domain. Okay, so that is key. So when you do your first derivative test, you are going to say your critical value is only 100 because that's what's germane to this problem. Okay, so now let's do our first derivative test. Okay, so I'm going to do first derivative. I'm going to put that there. Okay, so if I take a number less than 100 and I plug it in my first derivative, what's going to happen is it's going to be a positive number. If I take a number greater than 100, so say 101, and you plug it in the first derivative, you're going to find that you're going to get a negative number. Okay, so that means that our function, so the function looks like this. So I have a max profit occurring when I produce 100 units of the auto part. Okay, so let's write our statement. Okay, so I can say that at the CV of 100, the slope changes from positive to negative, which yields a max. All right, now, key thing. They don't want to know how many auto parts they should produce. They want to know what's the maximum profit they can get. So what you're going to do is this. You're going to say that maximum profit can be determined if I plug in the x equals 100, which was my critical value. That gives me a profit of $20,000, and that's what I would say for my max. Okay? So that's how we're going to do this. I only have one test I'm doing. I only did a first derivative test here. Every test has an explanation. When you talk about first derivatives, you have to talk about slope and then have a conclusion. And then make sure you are answering the question, because the question is not how many units should you produce. The question is, what will your maximum profit be? And that's going to happen when you produce the critical value number of units. Okay, so hopefully that's clear. And the difference with this problem also is that we had some embedded endpoints for my domain. Okay, let's go on to the second example. Okay, problem 2 is a pollution problem, and it says, okay, a marshy region used for agriculture drainage has become contaminated with selenium. It has been determined that flushing the area with clean water will reduce the selenium for a while, but it will then begin to build up again. A biologist has found that the percent of selenium in the soil X months after the flushing begins is given by this equation. Okay, so if that is the case, this is the equation we're looking for, we're going to be working with. What does this mean? So X is months, so X is going to be the months, and so we're analyzing this over 1 year span. That's why our months go from 1 to 12. All right, so that's important. This f of x is a percentage. So this is the percentage of selenium in the soil. Okay, so when will the selenium be reduced to a minimum? Okay, what does that mean? So they want to know when, so that's what month. Then what is the percent? So that's going to be f of the critical value of the month. Okay, so just like we've done before, when you're going to optimize something, that's a new word, you take the first derivative, set it equal to 0, because we're trying to figure out where max and mins happen. So in this situation, we have to do the product rule, the quotient rule. Okay, so we haven't done that lately. So you're going to say low d high minus high, which is x squared plus 36, d low, which is 2, all over low squared. Okay, low squared is 4x squared. So be careful with that. It's easy to make a mistake. Okay, so I'm going to start simplifying this. When I do that, I'm going to get 4x squared minus 2x squared minus 72. So, and all over 4x squared. And then my next step is going one more time. So that's going to be 2x squared minus 72 over 4x squared. Set that equal to 0. Okay, the only way that's going to go to 0 is if your numerator is 0. So set your numerator equal to 0. You get 2x squared equals 72. X squared therefore equals 36. So x equals, very carefully, plus and minus 6. Then you're going to omit negative 6 because it's not in the domain. Okay? You still should be solving for it, but then you're not going to use it when you do your your first derivative test. So your critical value that you will be testing is only 6, and that is within your domain. So we're going to put f prime of x up here, and if we plug in a 5 in the numerator, or in the first derivative, if you check that, you're going to get a negative value. If instead you plug in a 7, you'll get a positive value. So this is what your function's looking like. So we would say at CV equals 6, so this is month 6, the slope changes from negative to positive, and therefore that gives us a min. So to answer this first question, when will the selenium be reduced to a minimum, you would say at 6 months. And then to answer the next question, what is the minimum percent? You have to figure out f of 6, and you end up also getting a 6, but now it's 6%. So 6% is the minimum percentage that will be in the soil. Okay, so this is another application of taking first derivatives to figure out a minimization this time. Problem 1, we maximized profit. Problem 2, we minimized pollution, but we use the exact same technique. Okay, let's do one more, and that one's about salmon. Okay, in this problem it says we're going to talk about salmon spawning, and the number of salmon swimming upstream to spawn is approximated by this equation right here. That's the number of fish going up. Okay, so, and that number, let's see, X represents the temperature. So you have a domain restriction for temperature. Okay, so that should make sense to you. Clearly the water is not going to be either freezing cold, or frozen for that matter, or boiling hot. All right, so you're going to have a limit as to what your temperatures can be. That limit is the domain. So they want us to first off find the water temperature that produces the maximum number of salmon swimming upstream. So you're going to find the X that makes your number of salmon swimming upstream the highest. So you're going to maximize your salmon population of spawners. Okay, so to do that, you're going to do what we have done repeatedly, take the first derivative. Okay, so when you take the first derivative, you should be trying to do this now on your own, just looking at that equation. It's a pretty basic one. You're going to get negative 3x squared plus 6x plus 360. Okay, so you're going to have to set this equal to 0. What I would highly recommend is that you factor out a negative 3. That's going to get you x squared minus 2x minus 120 inside your parens. Then you're going to factor what's in your parens. And that's going to be an easy factoring problem, x minus 12 and x plus 10. So your critical values are going to be 12 and negative 10, and you have to omit because it's not in the domain, okay? So you're going to omit the negative 10. So when you test, you're only going to test the 12, and the 12 does indeed fall within your domain restriction. So 12 is the temperature of the water in Celsius, and we're going to figure out, does that give me a maximum population or a minimum population? So if you plug in an 11 right in here, and don't ignore this negative sign, it's going to be very, very important. Okay, plugging in an 11 here makes this negative. That's going to be positive. Negative times a positive is a negative, but then times the other negative makes it a positive. So this is a positive. If you plug in 13, you're going to get a positive here, a positive here, and then the negative in front makes the whole term negative. So this is what your function is going to look like. And remember, the top line was your first derivative test. Okay, so, and notice that I did not test the negative 10 because that was not in my domain. So you would now say, so let me just erase that. And I would say at a CV of 12, the slope changes from positive to negative, and that gives me a max. Okay, so 12 degrees Celsius answers the first question. Okay, the second question says, how many salmon will this maximum population be? So you're going to take your function, and you're going to plug in a 12 for your x, and you should get 8,024 salmon going upstream. So then they ask us to convert this temperature that you got to maximize the population, and that temperature was in Celsius, to Fahrenheit. So to do that, you would look up the formula, and you would find that Fahrenheit degrees equals 9/5 times the Celsius degrees plus 32. So you're going to plug in your 12 here, and then you're going to add 32 to it, and you end up getting, let me just move my thing down. Okay, what do you end up getting? Let's see. Okay, so after doing that math, I'm getting a temperature of approximately 53.6 degrees Fahrenheit. Okay, so we had to answer questions, and you had to do a temperature conversion. So I hope that's all makes sense to you. So again, it was a first derivative test with an explanation, and then make sure that you answer all the questions. Okay, let's go on, and we'll do the next page of the notes. Okay, in the 2.4, we're really just doing more of the same. So I've picked this problem to be able to go over both the first derivative and the second derivative test. Okay, so, and I'm going to really focus on plotting a curve. So that means you have some landmarks. The landmarks will be your max, your min, your y-intercept, and your inflection point. Okay, so that's just looking ahead. It also says round everything to the nearest tenth. So if I say that, you really want to do that. Okay, so first off, it says given this cubic function, okay, what is the y-intercept? So you get your y-intercept by plugging in a 0 for the x's. And when you do that, you get a point of 0, 1. And this will be one of the points that you're going to be plotting. Okay, that's a landmark for you. Next, it says find the critical values by taking the first derivative, setting it to 0, and solving for x. So in this problem, I'm also explaining the steps that you take. Okay, so I take my first derivative, and it's going to fall out nicely to x squared minus x minus 6 equals 0. So that's easy factoring. You get x minus 3 and x plus 2. You don't have any domain restrictions here. So your CVs are going to be 3 and negative 2. Okay, so that's what we have so far. We've answered the question for A, moving on to B. Now it says find the critical points by plugging in the critical value and solving for f of x. And again, I tell you to round to the nearest tenth. So when you do that, you're going to say, what is f of negative 2? And you're going to end up getting, rounded to the nearest tenth, 8.3. Then find f of 3, and when you round that to the nearest tenth, you get negative 12.5. So then you would report that your critical points, okay, because points are x and y values, are going to be negative 2, 8.3, and 3, negative 12.5. Okay, and that satisfies question B. Okay, so now we're going to go on to C. C tells us to conduct a first derivative test showing the chart and making your statement describing how slope changes on either side of the CV. So again, I'm telling you what to do. So I'm not going to tell you what to do on the quiz, but you should internalize these questions so that you know what your procedure is going to be. So get your line. This is where you're going to test f prime of x, and I put my critical values on my number line, and I check on either side. So I'm going to check a number like negative 2. I'm going to plug that in my first derivative, and I find that I get a positive value. Then I plug 0 in, and I find I get a negative value. Again, I'm plugging in to these factors. Then I test 4, and when I plug in 4, I get a positive. So the pattern I'm seeing for my function is that it's going to be a positive slope, a negative slope, and a positive slope. So I know that my negative 2 gives me the max, and my positive 3 gives me the min. Okay, so the negative 2, 8 minus 3 is going to be a max, and the 3, negative 12.5 is going to be a min. Okay, and actually once you look at your y values, you can tell that you indeed do have the max and the min. So let's do our statement. Okay, so at the critical value of -2, slope changes from positive to negative, and therefore you have a max. Okay, next, at the critical value of 3, the slope changes from negative to positive, and therefore you have a min. Okay, so that satisfies steps C. Okay, on the next page we're going to do the second derivative test. Now I will tell you that on the midterm, the first derivative test and statement were very good, but a good handful of people had problems doing a second derivative test correctly and also having the correct statement. So let's go over that carefully on the next page. Okay, so I've copied down the first derivative test. I've identified again the critical values, and now I've done the second derivative. So to do the second derivative test, you are still testing the critical values. Do not test an inflection point. Don't even take the inflection point. So here I'm going to put f prime prime of x, and unlike the first derivative test, I do not test to the left and the right. I instead take the critical value of -2 and plug it directly into my second derivative. That's going to give me a negative number. Since it's negative, that tells me that it is concave up. Okay, then I take the critical value of 3 and plug it into my second derivative. That gives me a positive number. And since it's a positive number, remember these smiley faces and frowny faces? That tells me that it's concave. Oh, sorry, the first one was concave down. Lost my head. This is concave down. Good. And this is concave up. Okay, so now you need your statement. Okay, so you can say this is a perfect statement. F prime prime of -2 is less than 0. Therefore, your function, and what function am I talking about? I'm talking about your original function, your f of x, is going to be concave down there. That's going to give me a max. Okay, then continuing, f prime prime of 3 is greater than 0, therefore my function is concave up, and that's going to give me a min. Now if you look back at your part C, you see that it affirms what we discovered by the first derivative test. So to go over this second derivative test, you are plugging the critical value directly into the second derivative, and you're going to tell me whether it's a positive or a negative resulting number. Then when you do your statement, you are going to say f prime prime of the -2. Identify it as being either less than or greater than 0. You have to discuss concavity. Second derivative is not about slope, it's all about concavity. And you have to have a conclusion. Okay? So that is a key thing. And if you do nothing else with this document, make sure you completely understand how to do a second derivative test and how to make your statement so that you get full points for this. Okay, let's go on to the next question, which is find the inflection point and analyze the concavity of the function. We'll do that on the next page. Okay, so to find the inflection point, you're going to take the second derivative equation that you had, and the second derivative equation was 2x minus 1, set that equal to 0. Notice I'm not doing that when I'm taking the second derivative test. When I'm finding the inflection point, then I set it equal to 0. So I get 2x equals 1, x equals 1/2. Okay, so now they want you to find the inflection point, so that means that you also need to figure out what the y value is. So let's get that done right now. Okay, so to get that y value, you're going to take the original function and evaluate it at positive 1/2, and rounding to the nearest tenth, you should get 2.1. So your inflection point is going to be 1/2, comma, negative 2.1. Or you can make that 0.5, comma, negative 2.1. Okay, so what about the concavity? So think about this. My function is going to be concave down from negative infinity all the way up to 1/2, but not including 1/2. At 1/2, the concavity changes. So then it's going to be concave up from 1/2, not inclusive, all the way to infinity. And this is how you analyze concavity. Oops, excuse me. Okay, you tell me what the concavity is and where it changes. Your inflection point, or your inflection x value, is the turning point. So that's your limit. So it's going to be concave down one way up to that x value, and then concave up from that x value on up. Okay, so now we're ready to sketch it. So what points do I want to include? So let's list them now. So I know I need to have the y-intercept, that's 0, 1. So that's my y-intercept. Okay, then I have a max. So my max is at negative 2, comma, 8.3. That's going to be a landmark. I have a min, and my min is at 3, comma, negative 12.5. And I just found my inflection point. And that inflection point is at 1/2, comma, negative 2.1. Okay, so get yourself a little graph. Okay, and it's just going to be a sketch, so you don't have to be completely accurate. So let's see, I had to get up to 8 here, so 1, 2, 3, 4, 5, 6, 7, 8. I need to get down beyond 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So then I also have to go 1, 2, 3, 1, 2, 3. So your y-intercept is at 0, 1. So that point will be right there. Okay, that's 0, 1. Let me get rid of these other little points. Okay, so then the next one, negative 2, comma, 8.3. So say that's right there. Then I have a minimum at 3, comma, negative 12.5. Let's say that's there. And then my inflection point is going to be at positive 1/2, and then 2.1. So let's say it's there. So once you put your points on your grid, you should see that things will flow nicely. Okay, so that's a good sketch based on our analysis. So, in conclusion, you must know how to perform a first and second derivative test. You must know how to write statements for both of those. You must know how to find the critical values. Clearly, you have to know how to factor. You must know how to find the inflection point. You must know how to find the y-intercept. And you must know how to do a little sketch. And then you will be all set. So I hope this helped. So go back over the key points. Make sure that you could reproduce this on your own.